right, everybody, we are moving on to our second standard. We are now going to be working with radicals that have nth roots. So we're going to talk about what that means. So we're still going to be simplifying expressions. There's no solving. It's just going to be a matter of reducing whatever is put in front of us using the properties that we know. So that's exactly what we're doing. It's just going to be simplifying some nth roots today. And it would make sense to start with, what is an nth root? Well, we know what a square root is. A square root is when we take something and we're looking for a quantity that is squared inside of it to simplify it. It is a way of undoing an operation, like adding and subtraction can undo each other. Square rooting and squaring, the power of 2, undo each other. Well, cube roots are the same idea, except of course we're looking for a perfect cube that goes underneath. So then this would the outcome would just be the C, because the cube root undoes the power of 3. A fourth root will undo the power of 4. So I'll put a fourth power under there, leaving just the D. Now, what is that called? What is that number called? And we actually do not write anything when we're talking about square roots. It's the most common root, and it does not use this little extra symbol, but we call this the index. Okay, it's called the index, and it's really just describing the type of root that we're using. So if I put a 3 there, it's a cube root. What's important is that this is very different than this. This is saying 3 times a square root. That's multiplication. This is actually calling it a cube root. So you're going to have to be careful with your notation. It's a way of communicating. This is how we communicate in mathematics, is correct notation. So it needs to be clear to whoever's reading it, which is sometimes, well, most often me, and to yourself, what you mean. Do you mean 3 times a square root, or do you mean a cube root? So back to what is an nth root. An nth root is that we can actually have any type of root we want, that we'd be looking for perfect nths. So that's what's going to come here. So we're going to be talking about perfect squares. So it's good to refresh our memory on what our perfect squares are. 1 is a perfect square, 4, 9, I'm going in numerical order, 16, 25, 36, 49, 64, 81, 100. We might go on, 121, 144, 169, where am I at? That's 13. 14 is 196, 225, and after that maybe we would go all the way up to 400. That would be 20 squared. So these are just some common perfect squares that would kind of jog our memory. If I see the number 64, I automatically know that it's 8 squared. It's just ingrained in me. If I see the number 121, I don't think of it as 121. I actually think of it as 11 squared. So these are my perfect squares. Okay, perfect cubes. So we want to be more familiar with these. So 1 cubed is still 1. -1 is actually a perfect cube. So we can think of, because -1 times -1 times -1 is -1. 8 is a perfect cube, 2, 2, and 2, but then so is -8. So I'm going to stop writing the opposites, but we have to recognize that opposites are actually perfect cubes. That doesn't work for perfect squares because it's an even exponent, but it does work for perfect cubes. So then 3 cubed is 27, 4 cubed is 64. 5 cubed is 5 times 5 is 25 times, so 125, so you can do that. And these can continue. These are probably the most common ones, but it is good to maybe even explore what some perfect cubes are so that you recognize them. These are likely the most common. Now your nths are, well, if I see a fourth root, I might want to just generate some perfect fourths that might come into play. 1, of course, is a perfect fourth, and then 2 times 2 times 2 times 2, so 16. And then you may continue on from there. 81 is a perfect fourth if I was working with fourths. Now, I might be working with fifths or sixths or sevenths. So just generating a little bubble on the side of your work might just jog your memory as you're working through these. Okay, so let's get to some actual simplifying. We're going to do 6 examples today. And these are our first ones. The first one is a square root, and that means that I'm looking for perfect squares that fit inside of 32. Now, there's lots of different ways to do this. I'm going to propose one of them, and that is to write it out in complete prime factorization. That is 2 times 2 makes 4, makes 8, makes 16, makes 32. So that is the prime factorization of 32. Then I'm going to write out that I have x times x, which is x squared, and I have y, 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 y. So that is 5 y's for my y to the 5th. Since I'm working with a perfect square, a square root, then I should be looking for how many perfect squares I have. And I see that I have 2 perfect squares of 2, one of x, and 2 perfect y squares. Okay, so my partners there. Well, each of these produces a number that will go on the outside of the radical when I finish. So that means I have 4x y squared on the outside, leaving inside still a square root of 2y. So that is the simplified form of this radical here. Let's work on the second one. This is a cube root. So if you'd like to work with prime factorization, which is just one way of doing it, the other one is to identify any perfect cubes that are in there. I'll show you both ways. So for 40, I would write down, well, 2 times 20, but 20 is made up of 2 times 10. 10 is made up of 2 times 5. So there's my perfect, or my prime factorization. Then I have an m, and I have 4 p's. Since I'm working with a perfect cube, I need to be looking for groups of 3. So there's one of them, and here's another group of 3. So on the outside, I have a 2p, and on the inside of my cube root, I have 5mp. What's important to note here is that I also included the cube on the outside of my cube root. So we don't have to write anything when it's a square root, but it is very important to write it when it is a cube root or a fourth root or anything. So the other option for this one, let me change colors with the pen so you can see a second way of doing it, is to actually just think of this as 8, because I know it's a perfect cube, times 5. And then say, well, p cubed times p, and then the m. So that makes these the perfect cubes and these the ones that are not perfect cubes. So this then becomes the 2p, because if I take the cube root of perfect cubes, I just get the base, 2p, and then the 5pm or 5mp goes inside. So you can break them apart whichever way you'd like. Let's take a look at example 3. So here I've got 96. I'm going to go back to my blue pen, and I'm going to start breaking that down, some prime factorization. And if you need to use your calculator, there's nothing wrong with that. Like, you're working with a bunch of numbers that aren't going to be common until you start breaking them down. So maybe I'll just divide it in half, and I see that that's 2 times 48, and then I divide it again, and it's 2 times 24, and then I break it down, so this is 48. And actually, I don't like writing it like this, because then I end up seeing too many things. So those of you that made factor trees, I find them difficult, honestly. So it's 2 times 48, which then becomes 2 times 24, which becomes 2 times 12, which becomes 2 times 6, which becomes 2 times 3. Now, if you're not sure about this, 1, 2, 3, 4, 5. So 2 to the power of 5 in my calculator times 3 gives me 96. So I know I broke it down correctly. You can double check. So I'm looking for perfect fourths. So I have a group of 4, and my leftovers is right here. So on the outside is this 2, but I have to multiply it by the negative 5 that was already there. So it's actually a negative 10 and the fourth root of 6. And that's as simple as this one can get. The next example actually is a quantity. So I really have 4 of these things. So I have 4 of them. So it's not that I need to get inside of it. I just need to recognize that I need 3 of them, and then there's this one left over. So this is my perfect group right there because I want a cube. So if I take one of those and put it on the outside, because that's what happens when you take the cube root of it, but then on the inside I still have an x plus 27y. So it's an interesting looking answer, but it's still using that base. My base just isn't an m. My base is this entire quantity, so the entire quantity must come on the outside. Once again, I caution you to make sure that this looks very clear that this is a cube root and that that cube is not actually on the parentheses, that this is separate. So make sure that it's very clear in the way you're answering it. If you get sloppy, I won't know if you understand the concepts or not. It's not that I don't like your handwriting, it's that I really need to know if you understand where those numbers belong as a notation. All right, we don't have much left. We got these 2, and I just put them here because they look a little bit different. So let's start to break it down. This is -2 to the 3rd power. It is itself already a perfect cube. So I could write -2, -2, and -2. And then I've got 9 times 9 times 9 times 9. So I'm looking for perfect cubes, and I've got those, which means on the outside I have a -18 cube root of 9. Last one. This is a square root covering a cube root. So I need to go from the inside out. So you must start on the inside of this one. So my cube root of this isn't, I made up this problem, now I'm thinking it wasn't the best idea. Let me do it let me do it this way. Let me switch it. So switch this with me. We'll just make that the cube on the outside. So the cube root on the outside. So I have the square root of 81. We'll start on that. I'm just thinking as I'm picturing this in my head. Let's try it this way. So the square root of 81 is 9, but it's still inside of this cube root. And because 9 is only made up of 3 times 3, and I wouldn't be able to have that extra 3, that this is actually as simple as I can get it. I have to leave it as just the cube root of 9. There's no other way to simplify this one. For another, let's just throw a quick example that didn't take long here. Let's do the 4th root of the square root of, let's go big here. Give me a second. Let's go 1024. Okay, so it sounds like a big number, but it's actually a power of 2. So it's using base of 2. So if we were to break that down, let's just take the square root of 1024, and it comes out to 32. So the square root of 1024 is 32, leaving behind the 4th root of 32 because I have to start from the inside out. So this leaves the 4th root of 32 for me to break down, which I know is 2 times 2 times 2. That makes 8, makes 16, makes 32. So there is the 2 that goes on the outside, leaving behind the 4th root of the extra 2. That was a much better example. So hopefully you wrote that in. We'll call it number 7. And that's it. We're going to get more practice when we're together.